no backgrounded scientists, thorough brilliant, but they had a bias towards Newton's law. They wanted to save Newton's law and not the Maxwell's law. But Einstein did not do it like it just because he had a bias towards something thanks to his family background. Right? So to make it short, protect human brain into ভিন্ন. Therefore, different human brains can solve different problems. On top of that, there are so many problems that not one person can solve all, right? So we need a lot of people in science and research. Now, having said that, we have to think of the recent revolution in machine learning as some other type of brain. It doesn't think and work like a human brain. So for sure, it's going to solve problems that we humans cannot. So we have to think it as of a second brain or a second kind of being that is smart, that can solve problem, and our job is to take help with it and solve problems that we cannot solve. So deep learning, in short, DL is a subset of machine learning. What is machine learning? Yes. Say think of a computer system, and you have some information, and based on that you want to, you have a task. Say I'm gonna tell you what task is, and this task can be done poorly or nicely, right? So on this task there is something called a performance that can be measured. Okay, so let's call the performance as P, task as T, and information, when you have a machine and you expose it to the information, it gets experience, right? So call it P. So what is machine learning? A machine is said to be learning if its performance P on a given task T grows with experience E. If you expose it to some information, it gains experience, and you say what? Think about the case. Let's go for 400 years ago, right? Tycho Brahe spent all his life to collect all the information of the planetary motion. This was huge set of data, and Kepler took 20 years to find the Kepler's law out of it. Now a machine learning system can take like fraction of a second to find those laws, but Kepler spent 20 years. So the task could be to find a law, and the information could be the astronomical data, and the performance is how well it fits, right? How much is the error, right? So now in this figure there is a question of underfitting and overfitting. What's that? So now once again coming to the analogy of a human being, why do you think that best research work is done when you are young, but not young like 10 years old, when you are say in between 25 and say 45? Why Einstein, Newton, Feynman, Dirac, they did their best piece of work when they were not so old and not so young? Why? What do you think?
তখন ব্রেন পারফরমেন্স
Experience helps or not? But too much experience is bad. This is the point, and we also see that experience is not always good. You need a right balance between knowing and not knowing. If you know too much, you stop doing creative work. Okay? So this is the question of underfitting and overfitting. Underfitting is that when you are exposed to information and you learn from the information and you try to solve a problem, but you have not learned so much, right? Like say in a book, you have some problems, you have solved them, and then you are exposed to a different problem which is related. So if you have not learned the whole book, you cannot really do well, right? আমরা জানি যে আমরা প্রায় এক্সামের সময় আগের রাতে পড়ে আমরা এক্সাম দিই, যার ফলে কি problem আমরা ম্যাক্সিমাম সলভ করতে পারি না. This is an underfitting problem because you have not learned much. This is one kind of problem that your performance is not good. Then another problem is that when you learn too much, okay, you learn too much that you stop thinking outside the box. মুখস্থ বিদ্যার ক্ষেত্রে যা হয়, you just memorize everything, suddenly a new question comes and you are like that. তো আমরা যখন একটা মেশিন লার্নিং অ্যালগরিদমকে ট্রেন করি, we have to find the sweet spot between underfitting and overfitting. Do not expose it too much to the information. So রিয়েল ওয়ার্ল্ডেও তাই হয়. আমরা যারা সায়েন্টিস্ট, আমরা জানতে এক সময় এত জেনে ফেলি যে প্রায় ঘটেছে যে নোবেল প্রাইজ উইনিং ওয়ার্ক পিএইচডি স্টুডেন্ট এসে বলেছে যে এটা এরকম হবে, সে ঝাড়ি দিয়ে বের করে দিছে যে নো, ইটস রং. তাই না? লো টেম্পারেচার ফিজিক্সে যিনি পাইওনিয়ারিং ইমার্লিং ওনেস, তাই না, 1911 এর নোবেল প্রাইজ, তার যে পিএইচডি ছাত্র, সে কিন্তু পেয়েছে এটা ফার্স্ট, মানে সুপার কন্ডাক্টিভিটি ফেনোমেনন. সে যখন আসছে যে এই পেয়েছি রেজাল্ট, জানি দিয়ে বের করে দিচ্ছে. দিস ইজ রং. ও দুইটা বারবার সেম পাচ্ছিল, কনভিন্স হয় না. পরে কনভিন্স হয়েছে, বাট সে অথরশিপের ক্ষেত্রে আর তাকে নিয়ে নিছে. But this is one example where learning too much does not help. You cannot think outside the box and then you don't see what is going on. By the way, মনের দুঃখে সেই পিএইচডি ছাত্র পরে ফিজিক্স ছেড়ে দিয়ে সে একটা ইন্ডাস্ট্রি তৈরি করে, এবং সেই ইন্ডাস্ট্রির নাম হচ্ছে ফিলিপস. So he was also successful. Anyway, so all this এই জিনিসগুলো বলার কারণ হচ্ছে যে মানুষের ব্রেইন যেইভাবে কাজ করে, একটা মেশিন লার্নিং অ্যালগরিদমেরও অনেক সিমিলারিটি আছে. The good side is that it can learn very fast, right? মেশিন লার্নিং এর কয়েকটা ধরন আছে. How much time do I have? When should I finish?
Whenever you feel like finishing.
So, supervised learning, unsupervised learning, and reinforcement learning. So, অনেক সময় এইরকম হয় যে ডেটার লেভেল থাকে, তাই না? মনে করো যে আমি প্রেডিক্ট করতে চাচ্ছি যে ফার্স্ট ইয়ারে যে 200 জন ছাত্রছাত্রী ফিজিক্স ডিপার্টমেন্টে ভর্তি হলো, বর্তমানে এনরোলমেন্ট কিন্তু 100 জন ছাত্রছাত্রী এনরোল করলো তারা কি সেকেন্ড ইয়ারের আগে ড্রপ আউট করবে কিনা প্রেডিক্ট করতে চাই হাউ ক্যান আই ডু ইট ওয়ান পসিবিলিটি ইজ যে আগের ইয়ারের রেকর্ড রাখা লাস্ট 10 ইয়ার্স 20 ইয়ারের রেকর্ড যে এই ছাত্রছাত্রী আসছে তার ব্যাকগ্রাউন্ড এই এইচএসসি এসএসসির জিপিএ এই তার জেন্ডার এই তার গ্রামের বাড়ি এই তার আর্থসামাজিক পরিস্থিতি এই সবকিছু নিয়ে তার এই একটা যদি ডেটাবেস তৈরি করা যায় দেন you can expose a machine learning algorithm to it and it can learn. So this is supervised learning where every student has a profile and there is a target variable whether the student will drop or not drop. It's a binary variable 0 and 1 and you train based on that and then you can use this to predict for the next year. এই ছাত্রটাকে ড্রপ করবে কি তাহলে ওই ছাত্রকে আমরা টার্গেট করে তাকে মোটিভেট করতে পারি পার্টিকুলারলি টার্গেট করে যে ডোন্ট ড্রপ রাইট সো ইট মাইট ওয়ার্ক সো দিস ইজ সুপারভাইজড লার্নিং ওয়্যার দেয়ার ইজ এ লেভেল টু এভরি স্টুডেন্ট in the past student X dropped student Y did not drop so there is a label and when we train like this it's supervised learning unsupervised learning does not have a label, right? For example, in a class of 100 students, you want to group them in a particular way, based on many things, based on religion and socio-economic status. সে হলে থাকে কি থাকে না সবকিছু নিয়ে you can make groups of them so you can check যে সব স্টুডেন্টের সব ক্যারেক্টারিস্টিক একরকম না so you can group them in different groups and find different characteristics of each group and to try to understand what is their need how we should deal with them in a particular case or whether they might be having some problem right so this is the case of unsupervised learning where you do not have labeled data or you just want to group some sample points right last but not the least we have reinforcement learning which is different which does not need any data at all so reinforcement learning is some sort of self learning you tell the algorithm the rule of the game and it learns by itself from the rules so one example of this is the alpha 4 right and alpha go and alpha 0 all these are by deep mind so what is this this is the alpha 4 that got the chemistry Nobel Prize this year so is unsupervised learning we just gave the system a huge number of protein structure and asked it please understand the underlying rule we don't know the rule so it worked it out but I am more excited about this alpha 0 says I play chess so alpha 0 is a reinforcement learning chess engine that we just gave the system the rules of chess that chess is played like this 64 squares and bishop moves like this knight moves like this so and what the system did that it played chess with itself to see what is the best way of playing right so and in 4 hours of self play it crossed the best human being it reached superhuman level in 4 hours time of self playing so this is an example of reinforcement learning where the machine learns on its own given some rules and some goal the goal is to win a chess game so one surprising thing is that we humans are writing down chess theory for the last 500 years or so, and the Alpha Zero does not play chess like we humans. It breaks all rules that you learn as a kid from textbook. The grammar is violated like hell. It's a big no when you go to a chess school. They will tell you don't play like this. You're gonna lose, but it means. So it means that we humans have explored a very tiny corner of the phase space of the chess, and it has played much more games, so it knows much more than we do. So for a task like playing chess, we humans cannot compete with machine learning. Yeah, and that's a fact, and you need to live with that. Okay, so that's a quick intro to machine learning. Now, coming to deep learning, which was the topic of the Nobel Prize of this year in physics. So deep learning is a subset of machine learning where we use artificial neurons. So now comes deep learning and artificial neuron. Okay? Or from that artificial neural network, or for short ANN. What is it? So we humans have realized that human brain is amazing, right? It can do amazing tasks. How long it takes for a kid to learn what is a cat? How many times you need to show to a kid that this is a cat, and the kid knows that it's a cat? Tell me. Think about it. Few times? 1,000? Once, twice, right? So why does the kid learn so fast? What is a cat? And then if the cat is under the bed, it knows that's a cat. If the cat is inside a box, it knows it's a cat. So human brain is amazing in certain tasks, like recognizing an object. When it's there, we learn really fast. It is probably because we humans are born with some biases in the brain. When we are born, we already have those biases in our brain, so it does not take us long to recognize an object. A few times you teach and it's done. Okay? So, but then since the human being is so good in particular tasks, scientists like in the 1940s and 50s, they tried to create some machine learning algorithm that mimics the human brain. Okay, the way the neurons work, and that's why it's called artificial neural network. So first, let's see how a neuron looks like. Here I cannot show the slide, so I have to draw a neuron, and forgive my bad sketch. Okay? So let's think. Then neuron cell is something like this. It has some inputs coming in, and then there is something called an action helo, and then from there goes some output. So what happens is that these are called who had biology here in huh? Dendrites, yes, Dendrites. Sorry? Let me write it like that. Dendrites. So dendrites, they take information from other neurons, and what happens is that they add up somehow, and here the neuron cell process them somehow, take a linear combination of them, does something to it, and then the signal passes through it, and if the input combines to be below a threshold or it's not too high, this will fire. If not, it will not fire, right? So and from here it's called an action healer, right? And what is it called? Is this called an action or what? I forgot actually. I am not from biology, but I am trying to pretend that I know. But I know. Action terminal there. Yeah. Okay, so yeah, that's it. It's really simple. You have a bunch of inputs coming to some computational core, and then computation is done, and then you send signal to the next, or you do not. It's just that. So based on this, we can create an artificial neural network ANN. So think of an input x1 and input x2 and a constant input 1. Okay? Now let's take them, multiply each input by a number. Let's call them weight. So this call it weight W0, this is W2, and this is W1. Right? So now you can write down this linear combination, call it Z, which is W0 times 1 plus W1 x1 plus W2 x2. Yeah? It's a linear combination of the two inputs x1, x2 plus a constant term 1. Now, what can happen here is that you can define a function f, call it an activation function f. Yeah? So now you can take f of z. So f of z. What comes out here, you can call it y. Or say y hat. Y hat is f of z. So what can happen is that you have a bunch of inputs, you take their linear combination and make this linear combination z as the argument of a non-linear function. This f does not need to be a linear function. That is the whole point. Because the world, the real world is anything but linear. Very few problems are linear in the world, and that we solve in our grade 8, 9, 10, and then not, right? So linear approximation works often, but most often does not, and this is just an approximation. Real world problems are non-linear, and the power of deep learning is that it is extremely non-linear model thanks to the non-linear activation function. Yes, you raised your hand.
Do we actually know it's linear or not? Or we are assuming?
The f?
No, the linear function. You are saying that it's a linear sum, right?
Yes, the fact that it's a linear combination, that is our choice, because we make the activation function non-linear. There is no need to make it a non-linear combination here, right? Yeah. Ultimately, all these non-linearities will be taken care of by the activation functions. And here I just wrote down just one unit of computation, but it can be billions of them. Like GPT has billions of these things, and in our brain we have billions of them, right? So when you take them in billions, okay, this is can perform amazing tasks. By the way, coming back to it, so the concept is that large number can do serious computation is something that we are understanding now. Do you know that in Brazil there are ants that live in colony, and they have hospital, they have drainage system, they cultivate, they have nurses, so on. It's an amazing work. But make it simple. Let's forget about the Brazilian ants. Think of the ordinary ant that you see in Bangladesh, have you noticed that the ants know what is the shortest path in three dimensions? For example, this room, if you have to go from this corner to that corner of this room in three dimensions, the computation of the shortest path is extremely non-trivial. You need to do calculus to solve this problem. But the ants know it. So how?
Spider also. Spider.
That's a very good question, and this is intriguing because it's thought that the eight arms of the spider, they each work as a brain. That's why it is so smart. The same with octopus actually, because the eight arms can take independent decisions. So it's like a network of brains, not just a single brain. So thanks for mentioning the spider. I actually didn't know, but the point is that individual ant has no clue what it means to be the shortest path. But you have to think of the ant colony as a fluid brain. Each ant is a neuron, and they can exchange signal like pheromone chemical they exchange. So when you have large number of interacting elements, there is a possibility that they will do smart things. And ants are smart, and you have to think of the ant colony as a brain, where each ant is a neuron. That's why ants can do amazing things. Okay. So now it's the same. Now we are understanding this thing. Likewise, the trees in a forest these days is there is this field of understanding in intelligence. There is a likelihood that trees in a forest can communicate somehow. There is a large number and can also do smart things. But this is not clear up now for ants. It is clearly known. So what happens here? You can have billions of artificial neurons that can talk to each other, and thereby they can solve amazing problems like this AlphaFold. So now the output that comes out of this computational box, let's call it y hat, and this y hat is a non-linear function, and this can be a function like this, okay? 1 plus e to the power minus z. So this is called as sigmoid function. Sigmoid function. When you make a plot, it looks like this. When z is minus infinity, this is 0, and when z is plus infinity, this is 1. Yeah. So it's like this, where this is 1. Yeah. So basically, if z is small, there is no output, 0 output. When z is large, output is 1. So sort of a binary output, like the human neuron. Okay, so it can be something like this. But then no one tells you this one is a single neuron. But then you can create a neural network. For example, you could say that why just take one? Let's take more here, right? Let's take 1, 2, 3 of them. Okay? So, and then you can connect each with each. Now, this will look like a mess with a single color. Okay, so each one is connected to each, and then you can from there take one more and then give a y hat. So this brings more non-linearity. This is say your input, and that's why we call this an input layer, and this is your output. That's why we call it an output layer. In between what you have will be called a hidden layer. Okay? So this is a deep neural network. It's a network of neurons, but not deep yet. It's a shallow one. When there are two or more hidden layers, this will be called a deep neural network. And when you use a deep neural network to train a system to learn something, it's called deep learning. It's as simple as that. But so sophisticated models can be very deep. It does not have to have two hidden layers only. So to come to the point of this year's Nobel Prize, this was given to one of them is Geoffrey Hinton, who is a computer scientist. Hinton. He is the person who made widespread use of a technique called back propagation. Back propagation. And this is one of the main reasons, main techniques why deep learning works so well, thanks to this back propagation. What is it? Suppose you are trying to learn what a cat is, right? Next time you make a mistake, you see a tiger, and you tell your mommy, "Mommy, is that a cat?" And mommy says, no, it's not a cat. So there is a backward loop. You are learning, okay, this is not a cat. Right? So you need a technique in artificial neural network as well to correct when it makes mistake, right? So when it predicts some number and then that number does not match, right? Suppose you want to predict whether a student will drop out next year or not. Even the features, x1, x2 could be all the different variables I mentioned, whether he or she lives in a hall or not, so on, so on, so forth. But then you have the past data and you know this student dropped or not dropped. So if this is supposed to be 1 for a particular student, but you do not predict 1, so you say, oh, there is something wrong, right? So how do you convey this information to the system that, hey, you did something wrong and you need to correct it? This is called back propagation. I'm not going to the math of it. It's simple. Leibniz rule, and Leibniz rule and chain rule are the same, right? Leibniz chain rule and concept of derivatives. Okay. There is a notion of loss function or cost function. You basically compute how much error you make, and then take derivative with respect to the outputs, and then see which way you should change your weights and biases. You remember I wrote these numbers, right? These are the model parameters that tells me how well the model will perform, right? When we change them, the performance of the model will change. But when you update them, given failure in some task, right? You say, oh, it's wrong. So then you use this technique to backward this information so that each neuron updates its corresponding weights and biases. But unfortunately, the human brain does not exploit this back propagation. Human brain uses something else that we do not know. What technique it used to correct itself once something is wrong. And if we can understand this, there will be a huge breakthrough in machine learning. Because the human brain does not need long to learn things like that. Still, if you want to teach a deep learning algorithm what is a cat, you need to give it a thousands of cat image. It needs thousands, but we don't need. And this is a clear indication that the human brain does not use back propagation. It uses something else, we don't know what. Okay?
So about the size. Because if you compare a cat with a tiger,
Yes.
size is a
But
they can do
what if I make it small? The kid can tell it in a book, right? A tiger and a cat side by side. There is a famous cartoon where there is a cat or a dog lying next to a door who has reads like that. Yes. And then the sunlight comes. So on the dog's body comes the stripes. Now you know this is a dog resting on the ground, but the stripes are coming from the shadow. But the machine learning algorithm will tell you it's a tiger. So it is tricky actually. So we need to understand human brain a bit more to have the next level in machine learning. Now, Hinton partially got the Nobel Prize for popularizing the back propagation. He did not invent it. That he is a powerful guy, and since he has power, he said, okay, this is good, and everybody used it. So it is good. Now, shall I stop here?
Yeah.
Hmm? So you want me to stop?
I thought that you said that enough is
Well,
enough.
this is not explicitly mentioned in the Nobel Prize thing, because he did not invent this thing, right? Okay, so I am going to the point where the explicit reason for this year's Nobel Prize is called Hopfield network and restricted Boltzmann machine. So these are concepts coming from physics, and this is an example of how physics is so powerful. You learn physics and you apply it in some other field, and that field is enriched. So the person who is the founding father of finance, was a physics student, and his father insisted that he does not do physics, he joins the family business. So he said, what shall I do? I want to use the physics concept in business, and he laid foundation to the subject of finance. So physics is very powerful, and wherever you use it becomes this thing. So Hopfield network, they come from, you might know this Ising model or spin glass system, for which there was another Nobel Prize a few years ago. Basically, this is connected to something called associative memory. Okay, so how does it work? You think that I play for you a very small piece of sound from music, right? Say take your most favorite artist, and I play for you 10 seconds of song, and you know what this song is, and you can sing the whole song, right? How can you do it? Have you thought that it's an amazing task? Because in your life, you have heard maybe thousands, if not more, 10,000 pieces of music, and then I play for you a very short sample of a piece of music, and you know what this music is. Do you think that your brain works like this? You take this piece of music and then you match it with all the music you have heard in your life, and then say, oh, the best match is that music, and that's why. No, you don't think like that, right? Somehow your brain reconstruct from this small piece the whole music. And that is the idea of the Hopfield network. Okay. Basically, you can have say you have a node x1 and x2, x3, x4, x5 and x6. So you have like 6 nodes and they are all connected. Okay. All connected with all. I don't know how many diagrams, how many. So it's like this. So
62.
yeah. So basically, when you have a network like this, all these things can have values. Say it's a spin system, so it can have value S2, it can have value S4, S1, S3, S5, and S6, right? So this could be binary values. So let's think. Let's think of this Si could be -1 or 1, yeah, or 0 or 1 if you like. So the contribution of Hopfield there is that he introduced a notion of energy. Okay, so the energy is defined as this: negative sum over omega ij si sj. Okay. This is this. And there is a half here. So what is this omega ij? This is just strength of the coupling. Take this x1, x2, I forgot these links. So take x1, x2. So the coupling strength between x1, x2, call it omega 1, 2. And one of the mathematical reason why this network works is that it is symmetric. If it was not symmetric, it would not work. I am not going to the proof of it. So omega 1, 2 is the same as omega 2, 1. So there are strengths, and I'm sure you see the connection with the
Ising model, yeah.
Ising model or spin glass system. It's just like that. So what happens is that when you have a piece of music, you can break it down in different bits, right? Or take a picture, you can break it down into different pixels. There could be n pixels and n bits of information. So you can put them all in these nodes as -1 and or +1. Say think about grayscale image. So -1 is black and 1 is white. Yeah. So what happens is that if you want to store this image there, what you do that you choose this omega ij such that this energy is minimized. Okay, and one way out to do this is called Overt or Hubbard, I forgot, Overt learning. That is that you choose omega ij equal to si sj. Okay, so if you choose like this will for sure go to the minimum, and this is a choice that is, since we know the S for a given bit number of pixels, this is a deterministic model, right? Everything is fixed. Next time you give some part of the image, part of the pixels, what it will do, it say you know S1, S2, S3, but you don't know S4, S6, S5. Like you give part of the image, not the whole, right? What it will do, it will try out different values for S1, S2, for these things to see what is the value for which this is a minimum. It will try to go to a minimum energy state, and in this way it can take an incomplete piece of information and make it complete. Okay, but here there are a lot of problems. One of the problems is that when you go to an energy minimum, if you store more than one image, right? So if you look at the space of parameters, you can have a value like this. Suppose this is the space of omega and this is the space of energy, right? This is the minimum where you want to go. But suppose if you wanna store in this network more than one piece of image, there would be more than one minimum. And one problem is that if you put too many of them, the minimum will interfere with each other and it's not gonna work. So there is a bound on how much you can put. But then there is also a problem that at a given point, if you give some incomplete information, it might be stuck in a local minimum and it does not jump to the global minimum. And that's where comes the Boltzmann. So Boltzmann is connected to bose. I have to connect my talk to bose somehow, right? So Boltzmann is connected to bose because both Bose, Einstein and Fermi-Dirac statistics, they jump to Boltzmann statistics at large temperature, right? So I am sure in future we are going to use Bose Einstein distribution and Fermi-Dirac distribution also in machine learning, but up to now, to the best of my knowledge, it has not been used. We are only using classical distribution, Boltzmann distribution. So what happens is that when you try a particular value of this S to make suppose I give you S1, S2, S3, S4 and you want to see what could be S4, S5 and S6. So what you do, you try with one particular value and see what is the energy value, right? And you change it and you try out. But the thing is that if flipping this reduces the energy, you do it, right? That's what you do. But when you use the restricted Boltzmann machine or in Boltzmann machine, you do not do it like that. You actually use a Boltzmann distribution. Okay, so you do it like this: e to the power minus e by sum over e to the power minus e. This is the Boltzmann distribution, right? So even if some value of S will minimize the energy, you may or may not take it. It follows a Boltzmann distribution. So it will not always go to the minimum, but most of the time it will go, and sometimes it will not go. It leaves room for creativity. And nowadays we use ChatGPT and all that. Thanks to all this foundational work, that because of the application of Boltzmann distribution, we can do so many things in deep learning now. This ChatGPT is underlying is physics actually. Yeah. One of the good things of this Boltzmann distribution, applying the Boltzmann distribution, is that when you are stuck in a local minimum, it can jump. Yeah, so this is one of the things. And then there was further improvement on this. let me finish with this, the concept of restricted Boltzmann machine, and then I can take some questions. So basically, this works a bit like the feed forward neural network I showed, X1, X2, X3, X6. Now you can draw here a bunch of hidden neurons that we call, and connect them. Okay. So there is no direct connection like the Hopfield network. There is no direct connection between the X, but they connect through some sort of hidden layer. So this is hidden layer. This is a visible layer. This is called a bipartite connection, because the neurons in the hidden layer, they do not talk to each other. They only talk to the visible layer, and vice versa. That's why it's called a bipartite network. And you can increase the number of hidden layers. So this kind of neural network architecture goes by the name of restricted Boltzmann machine, because you restrict them to be a bipartite graph. Okay, so this restricted Boltzmann machine is extremely powerful, and it has laid foundation to so many things. One of the major applications of the restricted Boltzmann machine is recommender system. You might have seen in YouTube, you watch a video and next time it suggests you something else. Underlying is this kind of algorithm. So I think, yeah, so this year's Nobel Prize was to Hopfield and Geoffrey Hinton, and because they have done this work, and I'm sure there will be more such Nobel Prizes in the coming days. So thank you for your attention.
The major advantages of this tech. Major advantages of this tech.
Because then when you have more and more parameters to play with, one of the things of the restricted Boltzmann machine to restrict is that sometimes you reach an oscillatory phase. You do not jump to the ground state.